It's like there are some comments or questions that when you open, is like opening can of worm, but we don't want to open can of worm, okay? We want to go with the specific questions, and I try to help you with each questions that you have. And if you ask your own specific questions, like how you could like answer this or what is the explanation, I'm sure if 2 or 3 of you ask your questions, it's common, same questions for everybody often, and the whole class would benefit from. The specific questions, what's the 3 to 5 questions, 3 to 5? What are those questions? Carmen,
that was two the part where you were comparing mixture A with mixture B to see the differences between the two of them.
I am really sorry. I don't know, is my computer or your speaker, your mic? I can't get the question clear. Possibly, can you type?
I will try.
I'm sorry. I like you guys to use the mic, but I couldn't get it. I don't know if the problem is my computer or your mic. Thank you. Okay, I'm waiting for the question. If someone else wants to ask, or you please continue typing the question. Okay. It was on a separate worksheet, and I did not really understand how to answer the question as I could not physically see what happened. Okay. If you could tell me, you're still talking about the comparing 2 test tubes, right? Okay, which 2 test tubes? Which chemicals? Which 2 test tubes, which chemicals? Please give me a question. So it was a different word or worksheet, the one that, are you talking about the announcement? This was a question, record your observation and indicate the type of change that occurred, chemical or physical. It doesn't tell you what chemical, okay. And you said, let me go back, I have to, test tube A and test tube B. Oh, thank you so much. That's now we're talking about, okay. So we have sodium carbonate in a test tube, and this is for test tube B. You're adding calcium chloride. And I am so glad that you're putting the phases for each of this reaction or chemicals. If you have AQNA2CO3, what does it mean? AQ stands for a soluble compound in water. And when you have just like salt water, it's clear solution. CaCl2, when it's aqueous, that also means that it's clear solution, transparent solution. When it's aqueous, that means just like you're adding table salt to water and you're mixing it, okay? You're mixing it. And then the other side of the equation, it says you have sodium chloride aqueous, but calcium carbonate is solid. So if calcium carbonate is solid, what does it mean? It means when you put calcium carbonate in the solution, it's not going to give you a transparent solution. It's going to make it cloudy. And when it turns cloudy or solid forms, that means a precipitate has formed. When a precipitate forms, that means there was a chemical reaction. How do we know there is a chemical reaction? We did talk about it last class during pre-lab discussions, that if a precipitate forms or a solid compound forms, that means it's a chemical reaction. So I was expecting you look at the phases for the reactants, compare the phases to product, and make sense out of that based on the 5 evidences for reaction. I gave just enough information for you to. I did not say that it did turn cloudy, but the solid, what's the symbol S stands for, means that a precipitate is forming, or a solid compound has formed. A solid compound that is formed is not a piece of rock. What it is like you mix the two clear solution that they both look just like water, and when you mix together, a solid compound appear in there, and it made the solution cloudy. And I hope that explanation, it's kind of makes sense at this point to you. And I was actually expecting that symbol of S helps you to answer that question. Perfect. Okay, is there another question? Sure. Is there another question? A specific question. You see, I was kind of waiting, not that I was trying to challenge you guys, but I was trying to say, when you send me an email, if you be a little more specific, then I can also answer your question faster and more specific. Okay, I did not get any email or response from you after I post that worksheet. I think I post the worksheet it was last week sometime, it was before the weekend. And if there was a part of the experiment that you couldn't get it, if you would have sent me an email and say, could you explain this part? I would have explained to you. I could have explained to you, replied to you, and also I would add something to announcement to make sure that other students, if there is any other questions, even though based on the chemical reaction, based on the symbols for the reactant and product, sometimes you can see that. The other equation, when it was magnesium plus copper sulfate, I put the colors for the reactants and color for the product. So since we only had 5 evidences for chemical reactions, and one of them is a color change, and the other one is the precipitation, one is change in temperature, one is change in pH. I'm sure if there was a change in pH or there was anything change in temperature, I would have included that in my response to, or in the chemical equation, like heat has been absorbed or heat has been released, something in that nature to help you to read the equation. Okay, I guess those are the 2 parts of the 2 parts, right? And did you get the answer to the questions you had? Did you understand how to? Nothing happens there. When you dissolve, that's just a physical change. because when you mix the sodium carbonate with water, a solution forms. It just dissolves. And the next step, which was adding HCl, when you add HCl, HCl reacts with carbonate. All carbonates, when you learn about different type of reactions, right now we are just learning about the evidence for the reaction, and in lecture, when you learn about different type of reaction, see that metals react with the acid and they release like hydrogen gas, most of the metals. And those are some patterns that you would learn. It's not like one rule fits everything. Even for when you learn this in lecture, you get like some hints how to predict a product. So when carbonates or bicarbonates, they react with acid, they release CO2 gas, bubbles form. Because it's a displacement reaction, it gives you carbonic acid. Carbonic acid is not very stable, and it dissociates the water plus CO2, and it forms bubbles. So when you add sodium carbonate to water, it's just like adding salt to water and mixing it. What happens? White crystals of salt would dissolve in water, and then you have clear solution, and that's all you had. There was nothing there to really mention it. And second, on the next step, when you add HCl, then you had a reaction that bubbles formed. So as I said, if there was any other any problem, I would first of all go back to theory of the theory part of the experiment. Read the entire experiment. Please do not just watch the video and think that it's you're set to go, because the video is just like 40 minutes and that's not enough to help you to really understand. Read the experiment. That's why you have the ebook. Read the experiment, because what you learn here is going to help you with your lecture as well. And then if you read the experiment, you watch the video, you did not understand, send me email. So do not leave it for last day. Even last day, I didn't see any other than if we have lab today or not, we have meeting today or not. I did not see any email this morning that this part of the experiment or this part of the video, I have a question, I need explanation. And if you do, I promise I will answer your questions, even via email. Or even if it's just, a few minutes before the class. Okay, we are going to start the new experiment now. Unless you have questions. If you do have questions, post your questions in the chat. Use the mic. I will answer your questions before I move to the next experiment. And if you don't have questions, I'm going to move to the next experiment. Uh-oh. What's next experiment? Experiment 3. Move too fast, looks like. And what can help you all, because it's a video and then you have a Word document, if you can open both of them at the same time, and as you see parts of experiment being done, first of all, read the experiment before you start watching the video, so you know what to expect. And open the video, download the Word document. As you watch the video, write down the answers or the parts of the fill in the worksheet, which is the data sheet that you get in the Word document, and then go back to video. You don't have to watch the entire video completely first and then start filling up, because then it's not you know, assuming that you don't have access to video while you're answering these questions. So you do have access. That's where you have to go back and forth, watch it again, and then answer the question. And sometimes you don't find it. I'm glad that some of you found it early, and I got a few emails that it's not there. But it's not. This is not the case all the time. When I make a mistake like this, then I'm a little bit more careful, trying to make sure that every step is included in the video, which I'm glad it did happen on the second experiment, and that was the time that they actually told me there is no help to actually help me in the lab or do the videotaping. So I had to do everything by myself, prepare the equipment and chemicals, and perform the experiment, explain the experiment, and videotape myself. So it doesn't, you know, it doesn't go that smooth, but the fact that I was helping the students to stay home and learn from home, that was giving me enough energy to continue. Otherwise, this is not a job for one person. Okay, next experiment is the empirical formula of a compound. You're welcome. Empirical formula compound. What is empirical formula? So let's try to at least, you know, understand the experiment now. Please read the experiment before you watch the experiment, or before you know, to answer the pre-lab question, you are expected to read the experiment first. So if you go to the introduction part or to syllabus, it tells you one of the assignments for you for each week is to read the experiment, and then it tells you to turn in the pre-lab questions. And if you just open the pre-lab or download the pre-lab, try to find the answers for those questions, then watching the video may not help you as much as you like. And I would ask you again, please read the experiment before you write the answers to the pre-lab. It's not the grade that you're getting from the pre-lab only. It's like how much you understand the experiments, and if you can, you know, help me here to by answering the questions. Okay, Leah, could you tell me what's definition for empirical formula? What is empirical formula? And let me know if you're here first. Leah, are you here? Okay, what's the empirical formula? Garrett? Or Garrett, sorry. Garrett. Yes, what's empirical formula?
It's too much to type, so I'm just going to say it. The empirical formula is a compound or molecule. It's the simplest whole number ratio of atoms that make each element that make up the substance.
Perfect. So when you say a chemical formula, in the you have molecular formula and you have the empirical formula. The information that you get from a molecular formula, it tells you what type of elements you have in that compound and how many of each. So when you say H2O, that means that's the formula for water. It contains 2 hydrogen for every oxygen. The molecular formula for the compound is H2O. So that's it comes as a package. The other compound, like H2O2, hydrogen peroxide, and I have it here. Hydrogen peroxide, that's the molecular formula. And information that you're getting from H2O2 means that it tells you that you have 2 types of element. So first piece of information you get is how many different types of elements you have. It's 2 types of elements. One is hydrogen, one is oxygen. Second piece of information, it's how many of each. You have 2 oxygens and 2 hydrogen per every molecule of hydrogen peroxide. When it comes to empirical formula, for the empirical formula, that shows the type of elements, how many different types of elements you have. You have 2, hydrogen and oxygen. And what is the ratio of the number of each element with respect to each other? So in this case, for every hydrogen, you have 1 oxygen. And as long as it shows you that information, when you have that information, that means that you have your empirical formula. So you have the ratio. Now, if you have the empirical formula, how would you find the molecular formula? Danielle or Davis? Can any of you answer the question? If you have the empirical formula, what other information you need to find the molecular formula? Find the molar mass. Very good. You find the molar mass. So if you know the molar mass is found using like a machine is called mass spectrometer. Mass spectrometer, if you give the sample to that machine, it can tell you what's the molar mass for the compound. So molar mass in lab, you would learn that you can find by freezing point depression and all that, but they don't do that all the time. That would have been like a very historical and traditional way. Now, mass spectrometer, it can give you the molar mass for a compound in a matter of seconds. So you place your sample in the machine and you look for the molar mass, it would give you the molar mass in a matter of few seconds, less than 1 minute time. So when you have the molar mass, then you have the empirical formula. Let's say for molar mass for H2O2, when you use the machine spectrometer, you find it 34. And empirical formula that you find for hydrogen peroxide, you see that is 1 hydrogen for every 1 oxygen. You find the empirical mass. Empirical mass is like adding the mass of the element from the empirical formula. You have 1 hydrogen, 1 oxygen, and hydrogen is 1, oxygen is 16, 1 plus 16 is 17. 17 is the empirical mass. Molecular mass or molar mass for H2O2 is 34. Where do you get that? That would be given information to you. So you will have that piece. And if it's 34 is the mass for 1 molecule, and you know that you only have hydrogen and oxygen with the ratio of 1 to 1, then you divide the molecular mass or molar mass by the empirical mass, and you find an integer, like 34 divided by 17, that equals 2. Then that integer multiplied by number of hydrogens multiplied by number of oxygen, it gives you the molecular formula for your compound. So in order to find the molecular formula, you need 2 pieces of information. First, you need to know what's empirical formula for that compound. Second, you need to know what's the molar mass for the compound. Sometimes empirical formula and molecular formula are the same. So when you say H2O2, that's empirical formula. And molar mass for water is 18. That's 2 hydrogen, 1 oxygen. So it's 18 divided by 18, 1. So you don't have to multiply it. It's the same thing. So empirical formula equals molecular formula. Now, the H2O2 is empirical formula for water, also molecular formula. Can you have H1O.5 as the empirical formula? No. What's the problem with that? Definition, very good. Definition for empirical formula is the lowest whole number ratio, not just the lowest ratio, is the lowest whole number ratio. So fraction is not allowed. So you cannot have 0.5 in there. So even if it's like a C2H3O, it will stay like that. That would be example for empirical formula. It could be the molecular formula also, but it's example for empirical formula because you cannot simplify it further. But molecular formula for glucose is C6H12 is a carbohydrate, carbon, hydrogen, and oxygen. C6H12O6. That's molecular formula. We know it's molecular formula because we can simplify it. If you divide all the numbers by 6, you get C1H2O1, and that is empirical formula for glucose. So you have to pay attention. It's like it's one short definition, but it has a lot of meaning, and that's like kind of scientific, and that's how scientists, they come up with the definitions. It covers a lot of meaning beyond it. So if you miss that whole number from the definition, then you're not going to get the empirical formula. You might get just the ratio, but that's not empirical formula. If you express your empirical formula with decimal points, that means you have the ratio, but you do not have the empirical formula yet. Okay, the lowest whole number ratio, that's empirical formula. How do they find the lowest whole number ratio? There are a few ways, and I don't think that everything of that different methods to find the whole number ratio is given in this lab, because it confuses you more. At the higher level of chemistry, it covers more of the empirical formula, because when you finish, let's say, with the level of chemistry degree, and then you're trying to do research, you're trying to come up with a new compound, you're trying to synthesize a new compound, your brand new reaction, then you have to identify your product. And in order to identify your product, you need to know what's the molar mass for the compound, what's the empirical formula, you have to present it, you have to defend it. But anyhow, in order to find the empirical formula, mass for each element must be given to you, right? And what's the next step when you have the mass for each element? What's the next step to go to empirical formula? Jada? Divide by molar mass. That's what's the purpose of that? Divide by molar mass. Okay. What's the purpose of dividing by molar mass? You could still say it. Okay. To find the number of moles for each. Yes, that's right. Sierra. To find the number of moles for each element. Because you want to find the mole ratio, so you have to have mole for each one in order to find the mole ratio. And you want to convert the, very good. So you want to find the number of moles. In order to find number of moles, you need the mass for each element. You divide by atomic mass from periodic table, and you find the moles for each element. When you find the moles for each element, then you want to find the mole, that's the mole ratio, okay? That's the mole ratio. Then you want to convert that to lowest ratio, and in order to convert that to lowest ratio, you divide it by the smallest number. Very good, Bianca. So, and very good, Hannah, because you want to find the correct ratio. So you divide by the smallest number, that gives you the lowest ratio. The one that is divided by its own number, which is the smaller one, that usually comes at 1, and then everything else, it's proportional to that. So you have the lowest ratio. And at that point, you have to be careful. You want to make sure that there is no decimal numbers, decimal places. If there is a decimal place, then you have to work with the number in order to come up with the whole number ratio or the lowest whole number ratio. You want to multiply. Thank you, Ashley. You are going to multiply by all numbers by one digit or by one integer in order to come up with the nearest whole number. And that's like a pattern. Let's say you have, I'm going to put a whiteboard in my, room probably to write on the board, or I use the Surface next time. So when you have the whole numbers, or when you have the number of moles for each, you have to look at your numbers. If your number in the decimal points, you see like 5, so if it's like 1.5 or 2.5, what would be that integer that you're multiplying? All numbers. So if the empirical formula becomes like if the ratio is 1 to 1.5, then you multiply both of them by 2. Very good. Then you get the whole number. You take care of that decimal place. If the ratio is like the example on page 29, that is 1 to 1.33, that is like a perfect number. So 1 to 1.33, then you would multiply both numbers by 3, because you want that 0.33 to become a whole number. So 1.33 times 3, it is going to give you a whole number, and then the other number, it's already whole number, but you want to keep the ratio. You don't want to just multiply the oxygen by 3. You have to multiply the other one also by 3. Now, a good question came up. What happens if you don't have a like clear number, clear cut? If I see 0.5, that's a clear cut. I know I have to multiply by 2. If I see like 0.3 or 0.33, then I have to multiply by 3. If I see 0.25, I have to multiply by 4 to get to the whole number. Now, what happens if the ratio is for one is 1 and the other one is 1.09 or 1.5? That 0.09 or 0.1 or 0.15, those are too small to multiply, because if you multiply, then you have to multiply by 8 or 7 in order to get to the whole number. So in that case, if the number is on the paper, they usually present the numbers with the, if it's a problem given to you, like the pre-lab problems, okay? Pre-lab questions that you had. Those, if you do your calculation correctly, they always come up with like perfect numbers. But when we are in the lab, everything has error. You have to assume that you could have like personal error and try to minimize personal error. You could have instrumental error. So you try to minimize, but can you eliminate 100%? No. Especially if you are doing the experiment just the first time, you cannot avoid that. So there's always some experimental error. Let's say you were trying to measure the mass of the zinc, and the zinc was not completely dry. If the mass of the zinc is not completely dry, then you are going to record the mass of zinc higher than what it should be for mass of zinc. Mass of the iodine, you're trying to find the mass of iodine that reacted. Well, iodine sublimes very quickly in the lab when it's open. That's why we keep it in the test tubes, that is, the cap is closed. But still, some of that it can sublime while you are transferring. So the mass of iodine used, it's going to be recorded to the best of situation possible. So you would get the closest number, but it's not the exact number. So the numbers that you find in the lab, they require rounding up, rounding down. That's why you learn about those rules, how to round up or round down significant figures as the first experiment. So to answer your question, yeah, that was, I don't know whose question was it, but I can find out here, was if it's a 0.1 difference, what would you do? If it's a 0.1, you round it up. So you are going to round up the number to like a nearest whole number. So if it's a 2.1, that would give you 1. If it's a 1.1, 2, that would be the nearest whole number. So you can also round it up. So if you get a number that is 0.85, you would have to round it up to 1. If it's 0.9, 0.92, you round it up to the next whole number, 1.82. We don't have like a fixed number, so you round it up to the next. Yes. So you round, if it's a 2.96, you round it up to 3. So you round up the number that they are close to whole number, but there is no clear cut. Was it clear? So the clear cut is like 0.25, 0.33, 0.5, or a number close to that. So if it's a 0.35, that's still multiplied by 3. If it's a 0.27, that's going to be multiplied by 4. So if it's a 0.55, you multiply that by 2, and then you would round it up or round it down. Okay. Perfect. So we got about the definition for empirical formula, steps how to find empirical formula. This is on the paper. And to perform the experiment today and find the empirical formula for zinc iodide, we have to do experiment. So here, these are very generous. They say like 3.99. Of course, you have to round it up to 4. But even if it's like 3.8, you would round it up to 4. So what we're trying to find out as an unknown today is the empirical formula for zinc iodide. And that means if you have the ZnAIB, what are the values for A and B? How many zinc per how many iodide? So in order to find that, we are going to, first of all, understand the theory for empirical formula. Then we start with about 0.7 to 0.9 grams of iodine and about 0.5 grams of the zinc, but we have to record the exact mass for each one to begin with. So you have to keep track of the numbers. So in this experiment, you also need to watch the video carefully, because let's say you have 2 evaporating dish, and if you don't watch the video at the same time you're filling out your data sheet, or you don't write down numbers as you're watching, then it's going to be hard for you to match which evaporating dish goes to which line. So you want to make sure that you can you manage to get the proper data, which I trust all of you are very smart and you can do that. The only thing, there is really no shortcut, no fast forwarding on the video, even though it's kind of a slow motion. So the experiment, in the first part of the experiment, you're trying to heat up the evaporating dish. and you want to cool it down to room temperature. What type of impurities would be removed by heating up the evaporating dish? Can you kind of list or tell me what type of impurities you expect? Moisture, very good. So if the evaporating dish has been washed and is wet, you have to dry it well. If the evaporating dish has been touched and oil from skin is on it, or any other impurities that are volatile, when you heat it up, they would evaporate. They would go to like a fixed mass. That's what you want, because you don't want to have like a drop of oil in the evaporating dish, and later on when you are heating up, that oil is going to evaporate, so that's going to cause error for the mass of the evaporating dish. So you want to make sure to heat up the fire or heat up the evaporating dish in order to get fixed mass for it. So it could be moisture, or it could be any volatile impurity. If there is non-volatile impurity, if there is a stain that is really old, you can't get rid of it, but at least the mass doesn't change during the experiment. Then it tells you to cool it down to room temperature. What's the purpose of cooling down to room temperature? Jose or Sierra? Any idea? It may not explain anywhere, but this is the time to learn also. Why do we have to cool down the evaporating dish after placing in fire? You cool it down to room temperature before you weigh it. Okay. The mass of the hot object is different from the mass of object at room temperature. So as it cools off, is going to sometimes it absorbs some limited moisture from the air, which is not avoidable. You cannot avoid that. You cannot work under vacuum. So you want to be as close as possible to when you have your sample and the evaporating dish heating up. So if you measure everything at room temperature, then you are kind of canceling the error. You might still have some error, so there might be some moisture attached to the evaporating dish as it's cooling down at the room temperature, because the air, the atmosphere has some moisture, but at least is consistent from trial 1 to trial 2 to trial 3. We are not changing the environment. We are not changing the humidity of the room too significantly. And if it's not changed significantly, then it's going to cancel the error. So if you have the same amount of the moisture for empty evaporating dish plus your sample, then it's going to cancel, or it's going to basically tear up or tear off. You want to record the mass of evaporating dish with all decimal places that your scale shows, or the electronic balance shows, which is 3 decimal places. 0.5 grams. It says approximately 0.5, but you have to record the mass with 3 decimal places. So you need the exact mass of how much zinc you have started with. So you have to be careful with these numbers. Then you are putting your iodine, also measuring the mass of the iodine carefully. Empty test tube, subtracted from test tube plus the iodine. That gives you the mass of the iodine. I told you already, some of the iodine might be in the vapor phase already, because is iodine sublimes. And so if it's a vapor phase, it's not going to transfer into evaporating dish when you transfer it. So it could cause some error. That's why it doesn't matter who does the experiment. If it's not perfect condition, if it's not like right away measuring the mass of iodine or placing and then avoiding any sublimation and adding, your numbers are not going to become perfect numbers as a result of calculation, like the pre-lab questions or any numbers that you get in lecture. So it's the lab. So there are some experimental error, but we're trying to work with that experimental error, but at least do proper calculation. That's why you have to show your work. You should never give me an answer is S2O3. What is S2O3? You have to show your work. How did you come up with that number? Okay, any questions? Please read the procedure before you answer questions in the pre-lab. Read the procedure before you watch the video so you can make more sense out of the video, and you can catch any any missing parts. So you have the mass of the evaporating dish, you have the mass of the zinc, you have the mass of iodine that you start with, then you get it to react iodine with zinc. Iodine is a yellow color solid, and when you mix it with zinc and when it reacts, it changes to zinc iodide. Zinc iodide is colorless solution, so that yellow color should disappear. That means all of the iodine has been reacted. Which one is the excess compound in this procedure? For those of you who have read the procedure carefully, which one is the excess compound? Which one is limiting reactant? Do you know which one is excess, which one is limiting? Iodine or zinc? Zinc is excess. Zinc is excess, yes, zinc is excess, because when iodine, the color of the iodine disappears, that means all iodine has been reacted and you still have some zinc left over. So when you decant the solution, you are separating the zinc iodide solution, and what is left over is zinc. Because some zinc is left over, that makes it, to answer that question, that zinc is the excess compound and iodine is the limiting reactant. Javier, how do you know how much zinc is left over? What procedure you would do to find out how much zinc is left over? You have the mass of the zinc at the beginning, before mixing iodine, before the reaction of the iodine, and then you have the zinc that is left over, right? Some of the zinc is going to be left over. The difference is going to be the amount of the zinc that has been reacted. So how do you find the zinc that is left over? You separate from, you decant the zinc iodide, and then you left with the zinc, unreacted zinc in the evaporating dish. You dry it, you measure the mass, you find out how much zinc has been left over. You have to be careful. The mass is going to be mass of the evaporating dish and the zinc. So when you are recording your numbers, if you get more than 5.5 grams of zinc left over, then it's obvious that it's mistake, it's an error, because it's the total mass of zinc was 0.5 that you start with. So the zinc that is left over must be less than 0.5. Okay, you have to watch the video, you have to record your numbers and do the calculation patiently. If you have any questions, you're going to try to find it in the experiment. If it's not in the experiment, then you would let me know. The Fe, or iron sulfide. Iron is a transition metal. It could have oxidation 2 or oxidation 3. So you might have empirical formula for iron sulfide as FeS or Fe2S3. So if you get different number than what you were expecting, it's due to the oxidation number, because when the problem is given as a pre-lab questions, it's assuming that there is like no error, so your numbers should come like perfect numbers. And the same thing for here for copper. Copper has oxidation number 1, has oxidation number 2. If the oxidation number 2, it gives you this empirical formula, then it's going to be CuO. But if it's oxidation number 1 for copper, that means copper is 1 plus, oxygen is 2 minus. The combination has to be 2 copper for every 1 oxygen, Cu2O. They usually, it's not that day because I wrote the question. All the pre-lab, and even if I adopt the experiment from someone else, all the pre-lab questions and additional questions, I wrote them myself. So I wanted to give you a combination that doesn't give you like the more popular empirical formula, to make sure that you pay attention to the calculation and make sure that you trust your work and your calculation and don't go with what's more popular. Do you have any questions about the pre-lab by any chance? Okay, let's see. Is it okay if we solve the problem using the atomic masses on the periodic table, or we were supposed to use the ratio method? The steps are always the same. The steps are, you find you have the mass of element. When you have the mass of element, then you find the moles of element by dividing mass over the atomic mass, and it's always atomic mass. Like for oxygen is not. In one of the questions it says like iodine as the molecular. If it says iodine as molecular, that means I2. So you assume that iodine is I2. So, but for the pre-lab, you use the atomic mass from periodic table. Yes, Jose, you use the atomic mass from periodic table, and you find the moles for each one. You find the mole ratio, then you find the lowest mole ratio, and you want to make sure your lowest ratio is whole number ratio. So it's like 3 separate steps. I have some other questions here. I'm just going to read and to make sure that I answered the questions already, because they come with different chat. Okay, the data sheet briefly, and I have a question regarding one of the parts. When we are mass of the iodine that reacted, do we just subtract the iodine mass in the test tube from the empty test tube? Very good. Yes, Matthew. Yes, the mass of the iodine plus the test tube minus the mass of empty test tube, that gives you the mass of iodine reacted, because iodine was the limiting reactant, is expected to be consumed entirely in the reaction. On experiment 3, they go over how early chemists did without having the AMUs, but it did. Yes, now we have more power because we have the yes, we can use the other one. We can use the atomic mass. It makes it easier. Okay, any other questions that you might have? It's almost 1 hour. We had a little bit more of a discussions, which is good. I'm glad to answer any questions that you might have from the pre-lab, because this is the perfect time. I am sure there were other concerns, or other classmates, they had concerns about part of the data sheet or part of the experiment that they did not reach out or they didn't ask the question today. But when we talked about it, discussed, they got the answers and they got the explanation, and it benefits everyone in class. So during the pre-lab discussion is the best time to discuss, but you don't want to be beneficial to others only, because if the paper is due, you're submitting it before. That's why I'm saying if you have questions, make sure you ask during my office hours. Your lab is on Tuesday morning. My office hour is like 9 a.m. on Friday. So you can drop in a question then, and because the office hour is recorded, if I get like 2-3 questions, and that's where I make sure to put an announcement. If I see something, you know, I put an announcement, or I would post the recording into the announcement so you hear other questions. So if you cannot ask your question, you don't have a question right now during the pre-lab discussions, please bring your questions to office hours. More people is going to benefit from, and it's way before your paper is due, and it would help you and everybody else. Any questions? No questions? Okay. Please read the experiment, then do the pre-lab assignment, then watch the experiment recording, then go to the data sheet. If you go straight to data sheet, try to make sense out of the numbers, it may not work. Okay. Attendance, Hannah?
Here.
Thank you. Sahar? Sonia? Ashley? Ashley? Ashley, you answered one question earlier. Leah? Let's see if there is a connection problem for Ashley. No connection problem. So. Okay. Caitlin? Jennifer? Correct? Carmen? Danielle? Davis? Caden? Sruti? Kate? Bianca? Manisha? Jada? Jose? Jada? Thank you. Surya? Okay. Sierra, sorry. Javier? Lillian? Aisha? Matthew? Ria? Okay, perfect. Any questions for me? Okay. Thank you. Have a nice day. Thank you. And if you have any questions, you can stay. If you don't have questions, please go ahead and watch the video. If you haven't read the experiment, please read the experiment before you watch the video. And if you have, no, I did not mark you absent, but I didn't get a response, so I don't have it present either. I'm going to mark you present with late response. Do you have connection problem, Ashley? On my end, this site, it didn't show you have connection problems. I was wondering where you are. Okay. Bye, Hannah. Thank you. Oh, it did froze it. If you have questions, stay. If you don't have questions, you can start watching the video. Jada, you have a question for me? Jada?
Can you hear me?
Yes.
Okay, I didn't have a question. It's just my connection got bad and it like froze the whole computer. So I wasn't able to like type or anything. But no, I don't have any questions.
Okay.
Thank you.
You're welcome.